I'm A.Jenkins. I'm from INL, which is in the north of Portugal. And today I'm going to talk about something maybe slightly different to what people have already said so far, which is I'm going to talk about an emerging technology, and I'm going to sort of present it in a way of why I think it might be interesting to the neuromorphic community in the context of some European projects. So we all know that we all know that basically data is the currency of modern society, and we know that data has a life cycle. We know that first we need to collect this data, we need to sense it. From an edge processing paradigm, we want to process the data and we want to move the processing as close to the sensing as possible. We need to sense it, we need to process the data to make something useful out of it. Data needs to be secure, we need to transmit the data, and of course we need to store the data. And a lot of spintronics, which is the field that I'm in, has talked a lot about various different parts of this life cycle of the data: sensing, processing, security, transmission, storage, and others. And this led to this idea of this basically talking about spintronics technologies in this context, in the context of wireless networks, and came up with this idea of the SWAN, the spintronics wireless autonomous node. At INL, we focus on sensing and processing, and I think they're probably the most relevant for this audience. So that's what I'm going to talk about today. Okay, I think this is funny, but nobody else does. Don't be a technological martyr, choose spintronics, it's smarter. We have the AIC here, so some light propaganda. So if we're talking about an emerging technology, we're going to have to judge it based on certain keywords. Is the technology scalable from neuromorphics point of view? Is it multifunctional? Agile, spintronics harnesses a lot of magnetic properties, which tend to be very fast. So we tend to have quite fast processes. Reconfigurability, I'm going to talk about non-volatility later. We have lots of ways that we can introduce non-volatility in spintronics. Transferable, I'm not going to talk about it now, but every type of device I mentioned in the presentation is CMOS compatible, and we are actively working in integrating them with CMOS. So depositing the MTJs directly on top of CMOS wafers. So this transferability of spintronics is very important. And then, of course, if you want to make an industrial impact and have a footprint, of course, you need to be efficient and reliable. So at INL, we make MTJs. In order to make MTJs, so magnetic tunnel junctions, you need to be able to work in a lot of different length scales. So basically what these are is a thin film with lots of multi-layers, some of them magnetic, some of them metallic, some of them oxides. In order to have the good properties that you need sub-nanometer control of the thicknesses of the materials. Then we go into a clean room and we pattern these into nanopillars. Typically, we work in the tens to the hundreds of nanometers for the nanopillars. Then obviously you need to create vias, electrical access, either in contact pads or vias to the CMOS. And this is going to be more in the tens of microns or hundreds of microns. We do everything on 200 millimeter wafers at INL. And then obviously we need to integrate this with electronics. So then we can actually interact with the real world. So what is a magnetic tunnel junction? Super briefly. Basically, in its simplest form, it can just be thought of as two magnetic layers, one of which is fixed, so it's not going to move, and one of which is free, so it can move with an insulating layer in between. And I think of an MTJ as essentially a two-way transducer. So it's basically something that allows you to take magnetic phenomena and look at it electronically. So you can, for example, if this free layer, the resistance of this device will depend on the orientation between the two magnetic layers. So in this case, they're anti-parallel, so the resistance will be high. If they were parallel, the resistance would be low. So I can see the magnetism electronically. But also, if we apply electronic currents, we can manipulate this. So we can, for example, switch the free layer from a parallel to an anti-parallel configuration. So we can manipulate the magnetism electronically, and we can see the magnetic phenomena electronically. And there's, at least at INL, there's four main functionalities that we look at. So probably the most famous one is as a memory. So you can store memory here, the resistance of the device, depending on this. We have this hysteresis. So we have the ability to store memory and set the device either in an anti-parallel or a parallel. We also can use it as a sensor. So we can, if we have a certain, if our resistance has a dependence on, in this case, on magnetic field, we can use this as a magnetic field sensor. Also, we can explore these devices work in the dynamic regime as well. So in this case, if you apply a DC current to the device, you can actually make this free layer oscillate. So you get these steady state oscillations. So you get an RF power when you apply a DC current. Additionally, if you apply an RF current, you can force sort of resonant excitation in the free layer, and you get this rectification effect. So here you go from a DC to an RF, and here you go from an RF to a DC. So you basically have the memory, sensor, oscillator, and rectifier are the sort of four key functionalities. And the four keywords that I want to sort of repeat throughout the presentation that I feel might be interesting to the audience is that MTJs show properties, they show linearity, non-linearity, non-volatility, and natural frequency. So I think these are the sort of the four carry-through messages I will make throughout the presentation. Okay, so let's start with linearity. Why would you want something to be linear? Well, you want something to be linear if you want a sensor. So, for example, I was talking before, if our resistance varies as a function of the in-plane field, so for example, our free layer is moving as we apply a field, our fixed layer is fixed, we can have a very high precision magnetic field sensor. Additionally, because these devices work as rectifiers, which I just explained, if we apply an RF current, we can generate these dynamics in the free layer, and we can have this rectified voltage as a function of, for example, the power, the RF power at a specific frequency, so it can also work as a high frequency sensor. So at INL, we make a lot of these magnetic field sensors. So this is actually the typical MTJ stack. It's much more complicated than 2 layers, but you have all of these different layers which are there to basically produce this effect. So something that has the resistance as a function of, we have this linear region of resistance as a function of external magnetic field. Now, magnetic field sensors are very ubiquitous in society. For example, you have around 100 to 300 magnetic field sensors in most modern cars. And MTJs are a very high resolution version of this, right? So you have a much higher resolution than you would have in a Hall sensor, and they're much cheaper than you might find in something like so they have comparable sensitivities to things like squids and NV sensors being better, but being significantly more expensive. So this is something that you can implement in the real world. Why would this be interesting to a neuromorphics community? Because it allows us to gather a lot of data, basically. So I'm going to give some examples of typical real world scenarios that we're collecting data using these sensors, just to give you an idea of the type of thing that we're working on. So predictive maintenance. So this idea, this rather cartoony idea, is that this is a piece of equipment and a factory line, right? And there's different parts of the equipment. So for example, we have a red part, a purple part, and a green part. And all of these things are mechanically coupled, right? And the whole system is vibrating away. And what we're going to do is we're going to put a magnet on the side of this piece of equipment. And now the vibrations which are going on here are going to correspond to a vibration in the magnet, which is going to correspond to a change in the magnetic field. Now, I've already said we have this very high precision MTJ sensor, which we're going to put nearby. And this basically means that we can convert the vibrations to a change in a magnetic field, which we can then, using our MTJ sensor, convert into an electrical signal. Basically, this is a holistic, non-invasive, agnostic approach. So basically, we're just putting a magnet on here. We don't need to have a sensor located throughout all of these different things. We're just going to have one MTJ sensor. It's non-invasive. It's going to be outside of the system. And what's interesting is that what you find is that different components will have different frequencies of vibration. And so when you then start looking at it if you start looking in the frequency domain, for example, you can see that a peak corresponds to a certain component on the machine. So we have some real world data that was taken in a production line over here. And so this is a spectrogram. So basically on the x-axis, we have frequency. So we just have the different peaks evolving, and then the y-axis is time. So it's basically how the evolution of these peaks evolve with time. So you can imagine this machine is going, and then every time you see a chunk, you see a peak here, depending on which component is moving. And so basically, we were in the factory measuring this, and we measured it under normal operating circumstances. We then asked the operator to switch off one of the motors, and we can see that whilst a lot of the components, so it's just not the entire machine, but just one of the motors of a pump is switched off, we can identify its absence. So this idea of this frequency domain analysis is very powerful because it allows us to really, in the end, just see the observation of a certain component. And then we ask them to create basically an anomalous functioning sort of environment. So basically have a compressed air failure, so have low air levels. And basically now you can see that we start to see this effect. So instead of the complete absence of this peak, we now have a sort of like a poorly performing peak. Right, so this is the kind of data that we take. Additionally, we also have been measuring smart sensing, so we can sense the current passing in a wire, and we can detect the signals produced, again, non-invasively. In this case, we measure the electrical signals. And here, for example, we saw anomalous effects corresponding to actually thunderstorms. So when lightning was striking the power lines, we ended up seeing these anomalous lightning strikes. Additionally, we've started doing quite a lot of looking at in smart automotive detection. So for example, we put our sensor here and we have the cars going past and we're measuring the features of our vehicle. And so we can see the signal as the car goes past the sensor. We generate these kind of signals. And then at the moment we're starting to do some, you can see the numbers here, 8, 5. It's not a very large data set, but we're trying to build up this ability to process this data. And if anyone is interested, we've been putting this data online. So that was linearity. That was how we can sense a lot of data, and we're starting to do the processing, but how can we use MTJs for actual neuromorphic computing? So if we go from linearity to non-linearity, I've already shown this magnetic field dependence. You can see that we had this linear behavior, but actually we see this non-linear regime as well. Additionally, if we apply a bias current, we get, so if we just apply a bias current to our device, we have a linear regime and a non-linear regime. But we also have a lot of dynamic non-linearity in these devices. So as you apply an RF current, you can have basically a very small, you get a small linear regime, but then you end up with this very pronounced non-linear response, which we can see in a second. But the last one that I want to focus on is this non-linearity of the device when it's behaving as an oscillator. So in this case, we're applying a DC current to the device, and when the system is initially damped, and when our DC current generates a torque that is equal and opposite to this damping, we start to see the device oscillating. So we basically have this threshold behavior and then this nonlinear response afterwards. So we've been looking at how to use this nonlinearity in the context of neuromorphic computing. And the first project we looked at that in was a project called SpinAge. So in SpinAge, what we tried to do was explore this nonlinearity and also introduce non-volatility at the same time. And we did this using multifunctional magnetic tunnel junctions. So here, basically, by just changing the shape of the devices, we are taking a device that works as a neuron, and then by changing the shape, we can have it act more as a conventional magnetic memory. And so with this, we can create circuits which have basically devices operating as neurons and devices operating more as weighted memory cells. And so this is the kind of systems that we've been working on. So we have, here we apply the inputs to our memory cells, and then the current that arrives at our oscillator cell is going to depend on basically whether or not our memory cells are in this low resistive parallel state or this high resistive anti-parallel state. And basically, depending on the memories, we can create these different regions. Sorry, the yellow here is when the memory cell is oscillating. So we can basically change the critical current of our oscillating cell by changing the resistive state of the memory cells. This is nice, and it means that our device is working as this nonlinear oscillator. This means that so now we're going to the high frequency domain. The high frequency domain, we're using the nonlinearity of the threshold current, but we're not really harnessing the most out of this high frequency domain. And the best way to do that, well, why is the high frequency domain interesting? It's basically because because if you have devices working at different frequencies, you can encode information at different frequencies. So basically, if we have multiple neurons operating at different frequencies, we can now encode the information in the frequency. So if we have a device 1 that's operating at frequency 1, device 3 operating at frequency 3, we can put all of these signals on top of each other and send them through a common bus. And over here, we can have rectifier devices, and our device that's only at F1 will listen to, so our rectifier at F1 will only listen to the source at F1, and so on and so forth. So basically, this is a way that we can create networks where we can come up with very radically different architectures because we have this selectivity of the devices. Apologies. So anyway, probably haven't explained that very well. But the point is we have a series of neurons which have certain frequencies and a series of synapses that have different frequencies. So our neurons here have this nonlinear behavior that we've already discussed, and our synapses are basically just going to rectify, and we're going to end up with the sum of the chain. And our non-volatility in our system, where is the weighting in the system? The weighting in the system comes from the fact that we're going to shift the frequency of our synaptic elements. So if we shift the frequency, this means that we can we can weight our synaptic layer. But the question is, how do we do this in a non-volatile fashion? The point is, how do we introduce non-volatility into these devices? That's the conclusion I want to come to. And basically, when you apply an electrical signal to this device, there's 3 different types of phenomena or 3 different mechanisms in order to introduce non-volatility. So you can, if you have a current, it can become spin polarized, and you can manipulate, for example, the free layer with the spin polarized current. If you have a voltage, you can create these large voltages across this oxide, so you can manipulate the barrier. And of course, when you're applying this signal, the sample is going to heat up, and you have this antiferromagnet at the bottom, which has this critical Niel temperature. So you can actually manipulate that with temperature through these 3 different approaches. So if you basically, our free layer isn't actually uniform. It has this texture, this magnetic vortex. It's not really important. What's important is that you see this vortex core, which is this red circle. And basically, when we pass a current in the system, we can excite this vortex core. And if we excite it sufficiently, we deform it, and we can cause it to flip. So basically, if we look at this graph here, we have what we have on the x-axis is the frequency that we're exciting the system. And on the y-axis, we have the power at which we're exciting the system. And basically, at low powers, we see a linear, nice response. Then at higher powers, we see this nonlinear shifting in frequency. And then when we get to a certain threshold, we get this triangular region, which is the region at which this switching takes place. So basically, what we can do is by applying currents, we can manipulate the magnetic texture, and the different textures have different frequencies. Okay, so how do we introduce non-volatility into the frequency response of our device? We can manipulate the magnetic texture using the current by switching the magnetization. And this is very nice because instead of thinking of something more like a conventional crossbar array, again, because we're encoding information in frequency, we can manipulate specific devices. I didn't emphasize because somebody freaked me out halfway through my presentation. But each of these, we control these frequencies purely just through geometry, for example. So this has a smaller diameter, this has a larger diameter, for example. Now we can manipulate, we can connect all of our devices in series, and we can just switch a specific device using a specific frequency. So all 1, 2, 3, 4, 5, 6, 8, and 9 are just going to ignore this signal, but 7 is going to get switched by it. Okay, I'm not going to stop too long here, but basically we have seen that this MgO oxide that we use in our MTJs can work as a memristor. We get these filaments, we get these resistive filaments, and we get this, we can have this 10,000% resistive switching ratio, as well as maintaining the TMR. This doesn't happen in all MTJs, but it is possible to create these resistive filaments across the barrier. And then the last thing I want to talk about is just briefly this, what if our fixed layer wasn't fixed? How do we fix our layer? Well, basically, I told you at the beginning, we have one that's free and one that's fixed. Basically, our fixed layer, what we do is we heat it up in an oven and cool it down in the presence of a magnetic field, and that's what determines the direction. But actually, we can apply, when we apply a current, we can also heat it above its critical temperature, and we can reconfigure it. So instead of it pointing from left to right, we can get it to point from right to left. Additionally, we can go to sort of 3 dimensions. We can add more layers. In this case, we can add like a storage layer above, which produces an in-plane stray field on the free layer, which is essentially just acting as a non-volatile in-plane magnetic field. But we pin this, so it's not free, it doesn't move, it's fixed forever. So it's basically just a permanent in-plane magnetic field in the system. But if we, so basically what this does is just cause a shift in our transfer curve as a function of field. What we can do is we can reconfigure this storage layer. So we can actually reconfigure this layer just by applying a large enough current to reconfigure the system. And then very briefly, just to finish, instead of just thinking of our layers as being uniform in magnetization, we can actually create complex magnetic textures, and we can pin those magnetic textures, meaning instead of just having an in-plane uniform field like this or like that, we can actually have a completely analog in-plane uniform field. So basically, by manipulating these pinned magnetic textures, we can create a system. Over here is basically our synaptic element that can be reconfigured in such a way that is purely non-volatile. We're not applying a field. It's very stable. We basically change the magnetic state here, heat it up, change the magnetic state, cool it down, and then we've changed this state for good. And we can also do it to this bottom antiferromagnet, which strongly affects how the devices work as sources. Okay, so just to summarize that, we have a region at which we apply a current and we excite dynamics in these systems. Then we have this sort of training regime where we can reconfigure different parts of the magnetic texture. We can reconfigure the barrier, and we can reconfigure these antiferromagnets and therefore the properties of the entire device. And then if we go too far, we die. And I think it's important to remember that death awaits us all. So to conclude, I think I'll just conclude, right? I talked a little bit about sensing and a little bit about processing.
Thank you. I have a quick question on the sensing part. Maybe it's a bit targeted, but I'm curious about the setup that you had for anomaly detection.
Okay, thank you. That was the bit where he stood up, so I freaked out at that point.
So I'm curious, what are the additional benefits that you get from? I think I was thinking about the previous one with the with the vibrations. What are the benefits of going for this kind of configuration where you have a magnet that is essentially vibrating alongside all of the other sensors that are probably also vibrating, compared to having 3 IMUs or accelerometers, like MEMS sensors, in the same configuration as you have there?
So of course, this is I mean, the idea, I think there's a distinct advantage to it being holistic in the sense that, yes, of course, if you're in an environment where you can put an infinite number of sensors and you can collect infinite number of data, then obviously you would probably have more information if you put sensors, multiple sensors. This is perhaps more attractive in a situation, for example, a piece of machinery where it's very difficult to access parts of certain components of a printing machine or something like this. I wouldn't say that this has necessary, so you get information about the entire system. So that the holistic part is the non-invasive part. You are outside of the system. You don't have to go in. You don't have to change the, so I think there is definitely, I mean, a car has 300 sensors for a reason, because they want 300 sensors, right? We're not suggesting we just put one outside the car. But I would say that it really depends on the industrial situation. But basically, the main advantage is to reduce the number. you can only reduce the number of sensors because you have this frequency analysis, because otherwise it's just a big mess on top of each other. You don't know what you're actually measuring. But if you have a system where you have these different components at 3 different frequencies, and this works and it's non-invasive, then why would you want 3 different sensors on it? Oh, we got an answer.
Sorry, 5 seconds. I just like a quick. What I meant was replacing exactly the sensors you have with accelerometers. Would
Just
you get
here?
more accuracy?
You mean putting the accelerometer here or putting it here?
In the there where you're pointing at the moment.
Yeah, so I mean, I can potentially, with this non-invasive process, I could measure every single component in this entire system, and you would need to put a sensor on every single component in the system. So it's just a reduction in the number of sensors.
Wouldn't sound also be holistic and non-invasive and agnostic and somewhat selective?
I think people do it. I don't have any personal experience, but I believe that's also I think I believe people do it. Why this is better than that? I think it's down to resolution, but I don't want to make any bold claims. It's not actually. It's more the work of the group than me. But I believe that people do things similarly with microphones. But I believe the key advantage here would be the sensitivity and just not being maybe the background noise, your background being less.
So yeah, I was wondering, since you can sense even tiny magnetic fields, and these magnetic fields, they carry some energy, right? Can you try to harvest, let's say, this energy that you sense to power, I don't know, maybe a LED or a cell phone? Or
yeah,
from
energy harvesting is something that's come up quite a lot with these devices. The thing about energy harvesting in general is if you're competing with diodes and things like that, you have to be, basically, these things might have an advantage in a very, very low power regime, but then do they really generate enough signal to actually be meaningful is the question. So you end up in a scenario where you can outperform state-of-the-art rectifiers, but you can't meaningfully acquire enough voltage to actually do something useful. So that's, but people, I mean, there is some active work on.
Even if you have a million of them? Like...
Yeah, because then it depends how you connect them. I mean, in theory, you can imagine a world where it becomes efficient, but I have never actually seen it become more efficient than, well, efficient enough to generate enough voltage to do something meaningful. I can expand. So basically, we can do this in MDO. So if you have current-driven effects, you can't have your resistance to be too large because you end up damaging your devices. Whereas if you have, so when we are working in these current systems, we tend to make the MGO very thin. And if your MGO is very thin, then what happens is you normally have an irreversible breakdown rather than a reversible memristor kind of breakdown. So actually, the results that are presented here, why I was saying it only works some of the time, is because you need to make your barrier thicker. And by making your barrier thicker, the device resistance goes very large, which now if you're thinking about impedance matching to a 50 ohm load and things like this, and you're making a network of many devices, perhaps if you're doing resistive measurements, it's less challenging. But if you're interacting with if you're working in the RF domain, pushing the resistance of your devices becomes problematic. So essentially, we know that we can do it, but we don't know if we can do it in devices that have a resistance equivalent to something like 50 ohms. We know we can do it on something that would have more like maybe 5 kilo ohms or something like that.